Hello, welcome to Random Maths, where my hand with a black pen does random mathematics. Yeah, that's, I guess, a descriptive name. Oh, so I just, I didn't, this isn't my first time, but I did just watch the video on Parker squares with Numberphile. I've watched it quite a few times, and I have thought about generalizing the concept of Parker squares to where it's not just that one square that doesn't work, but a whole family of them with the same messed up quirks that are actually quite interesting. So, what is the original Parker square? For those of you that don't know, the original Parker square was made up of these numbers squared. Um, 20, man, that's unfocused. 29 squared. Um, 1 squared. Need to check the other side real quick. 47 squared. I have the notes written in a smaller hand. 47 squared. Another 1 squared right here. Over there is 37 squared. I like 37. So 37 squared. 41 squared. So this is 41. We've got our fifth number in the Parker square. And yeah, I'm bad at drawing this. So what? 41 squared. 23 squared right here. Another 41 squared. And 29 squared. 29 squared. So this is the original Parker square. If you don't know what it was trying to do, it was trying to be a magic square. And a magic square is basically a square of numbers. 9 by 9 is what he was trying to solve. A square of numbers where all the numbers on the rows add up to the same number. So same. All the numbers in the columns add up to the same number. And the numbers on the diagonals add up to the same number. So, and not only that, but all these same numbers equaled each other. So diagonals equaled columns and rows. Everything equaled each other. In the case of the Parker square, if you added up each of the, I'll get a different colored pen. If you added up each of the columns, you'd get the same number. If you added up, each of the rows, you do these one at a time, of course. If you added up each of the rows, you'd get the same number. But only one diagonal, and I'll actually check which diagonal that is real quick. Only one diagonal added up to the same number that everyone else did. And that number and this is the diagonal that is the same. And this is the diagonal that is different. Every single one of these rows and every single one of these, and this one diagonal in the Parker square, all of these So cyan equals 3051. However, if we look at 23 squared plus 37 squared plus 47 squared, I won't show the calculator, we get purple, or the different one, equaling 4107. So the problems with the Parker square, it's not the Parker square square is not a magic square because only one diagonal has the same sum as the rows and columns. Only one diagonal has the same sum as the rows and columns. Okay, and the second problem it has is that multiple numbers repeat. In a magic square, every number is unique. So with this, every number is unique. Every number in the square, is unique. Whereas over here, 29 squared happens twice. 29 squared happens twice. I'm going to do that to show it. 41 squared happens twice. And 1 squared happens twice. So, obviously, a Parker square is not a magic square because in this case, not every number is unique. But if we look at the two ways in which the Parker square messes up, you can actually make rules for Parker squares in general. A Parker square then would be defined as a square where only one diagonal has the same sum as the rows and columns, and where not every number is unique, or not every number is necessarily unique. I think that will work. So we can have identical numbers. We can have identical numbers. It's just that one of the diagonals has to be different from everything else, and one of them has to be the same as everything else. Okay? So, if we move from there, we'll also assume 3 as a third rule for Parker squares. Every number we use every number is a square of a real number, or not a real number, of a positive, integer. I for integer. So every number is a square of a positive integer. And if we got those three rules for determining what is and isn't a Parker square, then besides this OG Parker square, which I will rewrite, this OG Parker square, there is also two families of Parker squares that I know of with an infinite number of members. You may find these less interesting than the old one, but at least they are an interesting design. And the greatest thing about them is that they also don't need the numbers to work. So I'll show you my own version of Parker squares just after I refinish the OG. So, if we go off on this journey of Parker squares in general, using these three rules to determine what is and isn't a Parker square, we will find that if we just have a square filled of x squared over and over again, no matter what the number is not a Parker square. And why is this not a Parker square, even though it is clearly worse than the Parker square? Well, it's not a Parker square because both diagonals are identical. So, Parker squares, just as an extension of their rules, cannot be one number. If Parker squares are made up of one number, both diagonals are identical, and so it cannot be a Parker square. Is not a Parker square. However, if we have two numbers, we can make a Parker square quite easily. Just look at this one, for example. 1 squared, 1 squared, 2 squared, 1 squared, 2 squared, 1 squared, 2 squared, 1 squared, 1 squared. This is 1, 1, 4, 1, 4, 1, 4, 1, 1. If we add up the rows, that is 1 plus 1 plus 4, that is 6. Columns, 6, 6, 6. This diagonal, which is a mess, there. This diagonal is also 6, but this diagonal right here is 12. So it's a Parker square. Yay, we have identified a Parker square. But you may have noticed, and you may have not, we do not need these numbers to make a Parker square of this shape. In fact, we can use any number to make a Parker square, any square number, if we just put them in this, any two numbers, if we just put them in this format to make a Parker square. If we just do x squared, x squared. In honor of tic-tac-toe, I'm going to do o squared, and o squared, and then x squared, x squared, x squared. Okay, so this, and it's of course it's mirror, this layout right here, and it's mirror where the o squared run across the other diagonal. These two forms, in this layout, you can put any numbers in the place of x or o and get a Parker square. You do not need to use any particular number. So there is an infinite amount of these and an infinite amount of its mirror image. I like to call these bichromatic Parker squares. Bichromatic Parker squares. Bi, because there is two numbers, and chromatic, because any number can be placed in the variables on the layout, as long as those numbers are different. So we've got every possible number, just like every possible note on the keyboard, the chromatic scale. So it's a bichromatic Parker square. I will call this layout the Nulthus layout, as an homage to the book Warbreaker that uses biochromatic breaths in its magic system. So this is going to be the Nulthus layout. And there may be other biochromatic layouts. So there's that, and its mirror will just be the mirror version of the Nulthus layout. So this is like right Nulthus, and the other one will be left Nulthus. But we can modify this to get a trichromatic Parker square. So if we, I'm just going to write out the layout right now. So to get a Parker square, an infinite series of Parker squares with 3 colors, all you need to do the same layout trick. There are 4 different versions of this layout, because you can flip the O diagonal and you can flip the positions of the X's and the Y's. And this is also a Parker square. It is a trichromatic Parker square, because any number can be placed in the Y, X, or O sections of this square, as long as they are different from each other. So this is a trichromatic Parker square. I do not know what I want to call this. Let's see. Okay, its different rotations are going to be the 4 classical elements. So air, fire, earth, and water. This, I guess, would be the air rotation. But this is going to be the I just think this is funny. I'm going to call this the oxyox. The oxyox layout, which just sounds ridiculous, but I'm going with it. And the reason for that is because one of those rotations spells this out in its first 2 rows. Basically, if you rotated it 90 degrees, the way it currently is, if you rotated it 90 degrees counterclockwise, you see oxyox right here. Yeah, that's why it's the oxyox layout. So, why do these layouts work with every possible number? The reason is pretty simple. It's because in the case of the bichromatic layout, every single row and in one of the diagonals, you'll be adding 2 X's plus O. You'll just be adding 2 X's together and an O together. That is in this row, in this row, in this row, and all of these, and in one diagonal, you'll be adding together 2 x's and an O. Whereas in the other diagonal, you'll just be adding 3 O's. And those are most certainly going to be different. They technically may not be, I don't know, but I'm pretty sure they'll be different. And in this layout, you in every single row, you will be adding together an X and a Y and an O in some form. And of course, in the left diagonal, in one of the diagonals, it's going to be 3 O's. And that is why both of these formats work. It's just because of commutation. You're just setting it up to where you'll always be adding the same 3 numbers together, no matter what direction you're going. And that's, of course, an interesting property. Well, except in the case of one direction, in this direction, it doesn't work, sure. And one more interesting fact about these 2 layouts is that not only do they have one good diagonal when they're squares, but if you were to make these squares a torus, so the edges wrap, then they would not have one good diagonal, they would have 3. They would have 3 good diagonals and 3 bad diagonals, so they would be tridiagonal. I guess you could call these Parker toruses. So if you turn these Parker squares into Parker toruses, then these would have 3 diagonals that all add up where you are adding 2x plus O. And they would have 3 diagonals where you're not. And in the same case over here, you'd have 3 diagonals where you are adding together a, x, y, and an O. And 3 diagonals where you are not. But that is essentially all I can do. I have only figured out 2 layouts of Parker squares that produce an infinite amount of Parker squares. And there is still one thing I need to do. Just a small thing. Because I did tell you that these were chromatic, and I know that's partially a reference to music, but it's also not. Chromatic can also be taken to mean color. This is, I guess, these layouts of squares are the only time you can replace numbers with letters and they have the same properties as the squares with numbers on them. How do I explain that? Okay, essentially, these squares I just made, you could add up any 3 numbers together, and these, any number could be in the layout provided, so long as the properties of commutation apply, and it will be a Parker square. You can put any number in x, y, or O, and it will be a Parker square as long as the rules of commutation apply. And so that's, and because of that, you can also just replace the numbers with colors and say that the rules of commutative math apply to those colors, and it would still be a Parker square in some sense, except you're just striking this 3rd requirement. So if you strike the 3rd requirement and say that numbers can be colors, so numbers can be colors, you can paint a Parker square with color and not use any numbers. So yeah, that should be a good thing for you artists out there. And just filling up this bichromatic. Yeah. So, numbers can be colors with these Parker square layouts, and these Parker squares, there's an infinite number of them in the world of real numbers, and an infinite number of them in the world of unreal numbers and things that aren't numbers at all. So, yeah, do what you want with that. I find this to be interesting. I think if you generalize Parker squares, that really cool stuff can be made out of them. It doesn't just have to be this one thing that Matt Parker made once and failed. It can really look good. I mean, I think the pattern looks good. I'm not that good at filling things out, but I think I like the pattern. So I'm going to say, if you think about it a little bit and generalize a little bit, you can go from a failure to something that looks great. So, see you guys.